recording. Okay. In the last class, as we finished the external natural convection, and in this class we'll do the internal natural convection one. Okay, so if you want to see me. Okay. So today's lecture will be including two parts. Okay. The first half of the class, we will do the chapter 5, which will be the internal natural convection. The natural convection actually, happens inside a rectangular enclosure. The second part of class, we will move on to the chapter 6, which we were talking about the turbulence effects on the convection. So chapter 6 will be the introduction to the turbulent flows actually. Okay, so let's start from the chapter 5, which is the natural convection across a rectangular closure here. And this geometry shows that what the problem it is. We have a rectangular closure. We have 4 corners notated as A, B, C, and D. Okay, and the closure has a width W for the wall, side wall AD and BC, and also has a height H. Okay, so wall AB, okay, is maintained at a uniform temperature TH. High, H means high, H means hot, and the other wall D and C, CD, okay, wall CD is at a uniform low temperature TC, okay. Basically TH is larger than TC. And we have the fluids inside this enclosure is still, initially, and we have this enclosure, okay, has an angle phi, regarding to the horizontal direction, and we have this gravity vector on the vertical direction. Okay. So for this problem, we have the temperature side TH on the wall AB, and we also have the temperature side for the wall CD. But we do not we do not know what the boundary condition, thermal boundary condition on the BC side wall BC and AD yet. So there are possibly 2 typical boundary conditions can be used for these 2 side walls. Okay. So first one is that we can just simply consider that the wall BC and the wall AD, they are adiabatic, or they are thermal insulated. Okay, no heat transfer at all. So basically the temperature gradient on the normal direction to these walls is 0. Okay, this is one possible boundary condition we can use. The second one is that consider that these walls, instead of for the first cases that we consider all these walls is thermal insulated. For the second one, we consider that all this wall AD and BC, this wall is perfectly conducting, which means that their K thermal conductivity can go to infinity. So in that cases, that we can consider that the temperature distribution on this side wall AD and BC along this X direction. The X and Y notation is showing here. The X is on the width direction and Y is on the height direction of the enclosure. Basically means that if we assume that this wall AD and wall BC is perfectly conducted, that means that the temperature distribution along this wall AD and along this wall BC, which is along the X direction, will be linear. Okay, just the temperature is linearly changing from point A, which is TH, to the point D, which means that the temperature is TC. Okay, so this is the second case possible boundary condition for these 2 side walls actually. Okay, so we will thinking that we will try to see that what's the natural convection will look like in this problem. Okay, and so let's consider that when the phi equal to 90-degree cases. Okay, that means that 90-degree means that you just all the TH and the TC, because these two places with the uniform temperature become the vertical. So basically we have TH on the left and TC on the right. And because the left hand side has higher temperature, so from our external boundary layer for the vertical place, we know that we will have the flow going up, okay, due to the buoyancy effects. And after it reaches this ceiling, the top, it will go to right. And when it close to the wall on the right, because this temperature is low, so it will cooling down the fluid inside, and will forming another boundary layer for the vertical place, external natural convection boundary layer we have before. So the flow will going down. So this you can consider this just like a two vertical place. Okay, natural convection happens on these two vertical places, and it will form this circle loops for the flow streamlines. Okay, and if you consider the phi equal to 0 degrees, okay, so 0 degrees basically means that so it will be the hot wall will be on the bottom, and the cold wall will be on the top. Okay, and the hot wall will be basically will heat the fluid near the hot wall, and it will going up, and the cold wall will cool down the fluid close to the top and make it going down. So it will also will following this cycles of the flow path, and because the symmetry effects. So in here, I assume that they have two these big vortices actually. So the last cases is that you consider the phi special cases is that you consider this phi angle is become 180 degree. Okay, 180 degree means that just means that you have the hot wall on the top and cold wall on the bottom. Okay, and in these cases, because the hot wall is on the top, okay, it will become it will form that stratified temperature thermal layers. Okay, there's no at the steady state there will be no fluid motion in it, just like that the temperature close to the top. Sorry, the region close to the top wall, the fluid will have a higher temperature, and the fluid to the lower wall, the temperature has the region to the close to the bottom wall, the fluid will have a lower temperature. And at steady state, I'm saying that there's no velocity. That means that there's no convection, and the heat transfer will purely be conducted by the conduction. Okay, because there's no fluid motion, so it will be conduction actually for the fluids. So what the conduction means? The conduction means that in these cases, if we consider for the fluid, there are thermal properties, physical properties is constant, like the thermal conductivity K, density rho, they are constant. So in these cases, the temperature distribution for the fluid inside will be just a linear, okay, on this vertical direction. The fluid on the bottom will be Tc, and the fluid at the top, the temperature will be Th. So this is what means the pure conduction in these cases. Okay. But for the general cases, okay, if the phi is not either these three special cases, with just some angle, this will be the governing equation for the problem, where the Bosnisk assumption is already applied, approximation already be used. The buoyancy effect is given by this. And this is the buoyancy effects terms, and we have the continuity equation for UV. This 2D problem, and we also have the x momentum equation. For the x momentum equation, the buoyancy effect is related to the angle angle term cosine phi, and for the y direction momentum equation, and we will have the buoyancy term which is related to the sin phi. The last one is the energy conservation equation, and this k over rho cp is just alpha. And the boundary condition, okay. For the velocity boundary condition is very simple because that is all the boundaries are walls, okay. So that means that if we can, because of viscous effects, we can consider that there are no u and v velocity at all these walls. So on all walls, u and v equal to 0. This is boundary condition. And on the wall AB, temperature is fixed at TH. And on the wall CD, the boundary temperature is fixed at TC. So ABCD is notated in this picture. And for the side walls, okay, BC and DA, as we talked before, there will be two cases. If it's the thermal insulated, that means that there's no temperature gradient. Sorry, there's a typo here. Let me see. So it's not should not be equal to partial V. Okay, so this is not partial Y. It should be partial N. Okay, vertical. N means normal direction. Okay, and for the case 2, if this wall BC and DA, they are thermal perfect conductor. Okay, thermal conductor, and then the temperature will be linear distributed. Okay, on X location. So this will be their temperature distribution on these two side walls for the case 2. Okay, so now we want to solve these equations so that we can know that what the velocity and the temperature distributions will be. And after we know the velocity and temperature distribution, we will know that what the friction at the wall and what the heat flux between the wall and the fluid. There are so the first method to solve this governing equations is we can try to using the numerical method, which means that we can get exact solution by using those numerical methods. So for example, like the finite difference method. Okay, but before doing that, we can first do some pre-processing for the governing equation to make it easy to solve. Because that partial u partial x plus partial v partial y equal to 0, that means that gradient of the u equal to 0, which means divergence of the u is 0, which means that the flow is incompressible. And for all incompressible flow, we can just still introduce the concept of stream function, this phi, this side here. And the reason we introducing the stream function is that after we introducing the stream function to replace the velocity terms u and v, the conservation equation, the continuity equation will be automatically satisfied. What does that mean? That means that if after you're introducing this stream function, instead of solving these 4 equations, you only need to solve 3 equations because one of them will automatically be satisfied. Okay. And the second notation we can use is omega. Omega is let me write it here maybe. This psi is the stream function. And this omega is the vorticity. Okay. We need this omega here because that, as you already see that in this closed in this internal natural convection, we have all these vortices behavior, and the vorticity can be, the magnitude like for the, rotation of the fluids, to measure the rotation of the fluids actually. So this is the vorticity definition for this 2D case. Partial V, partial X minus partial U, partial Y. And this can guarantee that the positive omega direction will be the positive Z direction to satisfy the right-hand row. Okay. After we have this, after we introducing this stream function and vorticity notation, the first thing we can do is that we can try to remove the pressure term. Okay. So we have the pressure term on the X momentum, and we have the pressure term on the Y momentum. And we can just use I can just do this, okay? For the X momentum equation, we do partial Y on the both sides. And for the Y momentum equation, we do partial and partial X on the both sides. And we minus we subtract these two results actually. Basically that you do partial Y on this one, you do partial X on this equation, and using this first one minus the second one. And this will become partial P, partial X, partial Y, and this will also become partial P, partial X, partial Y. And after you do the subtraction, the pressure term will be removed. Okay, so this will be the results will be, and you can group them together, and by using this vorticity definition. So the final result will be this one. Okay, and if you do, and also that we're using this stream function to replace the U and V. So this will be the results, which only contain the phi, sorry, the psi and omega. Okay, and also that for the energy equation, okay, we can just simply replace the U and V with the stream function. Okay. And there is another correlation for the omega, because that omega is defined as partial V, partial X minus partial U, partial Y. You can just substitute this stream function definition for U and V into this omega definition. You will also have this partial square phi, partial X square plus partial square phi, partial Y square, it will be equal to minus omega. Okay. So after we do all this substitution, what does this mean? This means that before we do this conversion, the unknowns, okay, the equation we want to solve, including we do not know the U, we do not know the V, and we do not know the P, and we do not know the T, right? This is the unknown function before. And after we do this conversion, okay, and also we have like 4 equations, right? We have the one continuity, 2 momentum, and 1 energy equation. And after we do this conversion, we will have 3 functions left. Okay, we will have 3 unknown left. We do not know the psi, okay, and we do not know the omega, and we do not know the T, temperature. Okay, and we also have 3 equations, 1, 2, 3. These 3 equations left. Okay, so we have 1 equation derived from the momentum, and 1 equation derived from the energy, and 1 equation just the correlation between the stream function and the vorticity. Okay, and if you can even consider that the second equation is not an equation, because that you can just substitute this the second one, omega, into this the first equation. Okay, you can actually substitute this omega into the omega here, the omega here, the omega here, and the omega here, and make it only, you can even make it like the unknown is only phi and T. Okay, you only have 2 equations to solve. Okay, you can just assume that you only have 1 and 3. These 2 equations. This is just a substitution of omega. Okay. And So this is the results. Okay, we have two equations. The first one from the momentum, and the second one from the conservation. And we have two unknowns for this psi and the temperature. Okay. And what's the boundary condition for this, reduce the equation? When I say is reduced because that originally we have 4 equations, and now we only have 2 equations. Okay. So first, let's look in the temperature, right? The temperature boundary condition is still same as before. Okay, it's very easy. Sorry, it's very simple. But the boundary condition for the stream function is a little bit tricky. Because look here, because that because we have the velocity equal to 0 at all walls, right? U and V equal to 0 at all the walls, and also we know that so U and V can be calculated based on this stream function partial phi equal or partial y for U minus partial phi or partial x for V. Okay, so we can just think that okay on all walls the partial phi or partial x and partial phi or partial y equal to 0 because U and V is equal to 0 on the wall. We can do that, but this is boundary condition is problematic. Why? Because that for this problem, if you're using this boundary condition, you will see that all the boundary conditions for this psi stream function is in the derivative terms. Talking is on all the boundaries, you only have the derivative terms, or you can see that Neumann terms, type of boundary condition for the stream function, and this will make you unable to solve what's the absolute value of the phi, or absolute value of the psi. Okay. So what we will say, this will make the value, okay, of psi kind of arbitrary. Okay, because all the boundary condition is only in partial terms. There's no Dirichlet type of boundary condition where you give a fixed phi value at some point. Okay. Since only derivative of phi defined at the boundary. Okay, but this is but if we, if you, know that what's the meaning of the stream function, okay. If you took the fluid mechanics class before, and you know about the stream function, actually the absolute value of the stream function is not that important, okay, because stream function is you can consider is at some potential function. Okay, the most important things for stream function is the difference between the two psi value. The absolute value of each psi value is not that important. Okay, so that means that we can arbitrarily set an origin value phi equal to 0 value, for this problem. So we can, for example, let's set at the point of A, okay, psi equal A, psi of A equal to 0. Okay, so at this A point, this point of A, let's assume that this is the origin of the psi equal to 0 location. And because that on the wall, okay, you can consider that since partial psi and partial x equal to partial psi equal partial y equal to 0 along wall AB, okay, along wall AB. What does it mean? It means that along the wall of AB, there is no gradient in any direction for the psi. So that means that if you do integration, you can know that the psi and B, it has to be 0, okay? And similar things, okay? Since this one along B and C, you can also derive that psi of C will be 0, okay? And similar thing, you can do that because along the wall, we have this psi equal to constant actually along C and D. So you can derive psi and D at this point D equal to 0. What does it mean? This means that you can think that psi equal to 0 along all walls, right? So if we do this, okay, the advantage of this is that by setting this origin value, okay, we can get, when we do the numerical solution of these governing equations, we can get the definite value of this stream function psi. Otherwise, if you only have the derivative boundary type of boundary condition, you won't be able to solve the psi value by using the numerical methods actually. Okay, so by setting this, the boundary condition of psi at the wall can be converted. So this type, we will not using this boundary condition anymore. Okay, we will convert it. We will changing the boundary condition of the stream function will become on wall AB and CD psi equal to 0, and the partial psi, partial x. Partial psi, partial x is the normal direction for the wall AB and CD. Okay, let me confirm it. For the AB is this one, and x direction is here. Okay, so the x direction will be the vertical for this one. Okay, basically means that on the wall AB and CD, we set psi equal to 0, partial psi, partial x equal to 0. On the side wall BC and DA, we also set the boundary condition psi equal to 0, and the partial psi, partial y equal to 0. Okay, and you can even group this type of boundary condition of this psi boundary condition, into a much shorter one. You can just think that on all walls, psi equal to 0, partial psi, partial n equal to 0. N is the normal direction to the wall. Okay, so basically what we're doing here is that we have this governing equation, we have this temperature boundary condition, and we will have this new psi boundary condition for the stream function. Okay. All right. So there's an optional step here that before we using the computer code of any numerical method to solve that equation. We can first do non-dimensionalization. Okay, this is the optional step because that even without this non-dimensionalization step, you can still writing your own finite difference or finite element code actually to solve this equation with this boundary condition. But in here we do including this optional step actually, where you can do the non-dimensionalization for that equation. You can define a dimensionless stream function psi here will be the psi times Prandtl number divided by the kinetic viscosity nu. And you can define the non-dimensional dimensionless vorticity omega, okay, which will be equal to small omega times this W is width of the enclosure, width square times the Prandtl number divided by the nu. And you can define the dimensionless x coordinate and y coordinate by dividing by the width of the enclosure. And you can also define the dimensionless temperature, which becomes theta equal to T minus Tc divided by Th minus Tc. One thing you can see, you need to notice that here is that when we define the x and y, okay, we're using W, we didn't using the H. The reason is very simple, okay, because for the problem we have here, okay, we have the constant high temperature on this on the wall AB. We have the cold temperature on the wall CD. Okay, is this W will actually the gap between these two wall AB and CD actually affect the fluid, the natural convection inside the fluid more rather than the H. So that's the reason that we consider W as the so-called characteristic length scale for this problem, not the H actually, because this W is the distance between these two walls with this temperature difference. And we know that this temperature difference will drive the fluid actually due to the natural convection. And that's why this W is more important than H, okay? And W will be considered the characteristic length. And then in this non-dimensionalization, we're using W, that's the reason. And also even the omega here, we're using W, okay? After this non-dimensionalization, this will be the final non-dimensionalized form, okay? You have this omega to X, and you have, for this is the momentum equation, and this is the energy equation, okay? And you will see some dimensionless parameter. The Prandtl number is showing here, and the Rayleigh number defined based on the with W is showing here. This W means that it's using length scale for W, okay, Rayleigh number. Okay, and also you need to know that this inclination angle phi, okay, this angle phi here, and inclination angle phi here is also already a dimensionless parameter because we use angle, okay. And the boundary condition is also changed, okay, to the dimensionless form, okay. As x to 0 will be the hot wall, as x equal to 1 will be the cold wall, okay. Y equal to 0 and y equal to a will be the two side wall, and this a, okay, I didn't give the definition of the a. A will be equal to h divided by w, and this is the aspect ratio. Of the enclosure. Okay. All right. So and for the temperature one, okay, on the bottom on the hot wall we have theta equal to 1. On the cold wall we have theta equal to 0, and on the side wall y equal to 0 and y equal to a we have this either case 1, thermal insulation, or case 2, perfect conductor. Theta is changing linearly with x. Okay. As I already mentioned here, okay, this step of non-dimensionalization is optional, right? Because if you want to write a computer code, you can either write a computer code to solve this dimensional form of the equation, or you can also write your computer code to solve this non-dimensional form of the equation. Both ways are okay, but this is but both ways has some advantage, and some way has the other way has some shortcomings, okay. The advantage of to solve this dimensional equation directly is that it's very straightforward, okay, because you avoid an additional steps, and also that after you solve this one, your results will because after if you solve this equation, your result will be just the phi dimensional form of the phi and the omega and the t. Okay, your result will be directly the result you got is dimensional form. You do not need to do any post processing for your results to make it dimensional. Like so to solve this dimensional form equation directly, the advantage is that it's very straightforward. It can it's very convenient because and can save your time because that you do not need to do that non-dimensionalization for the equation, and also that after you got the result, you do not need to scale the result back to the dimensional form. You do not need that. Okay, and it's very straightforward, and that's why, because this is advantage. That's why that if you're looking that if you use any commercial software, those commercial computational fluid dynamics or computational heat transfer software. Most of them is going to try to solve this dimensional form equation directly. Okay, and because that the developer of those commercial software, they want to make their software easy to use, and this form is more easy to use, easy to solve. Okay, this is the advantage of the dimensional form. But okay, the dimensional form, what's the disadvantage of this dimensional form to solve this dimensional form directly? Is related to what's the advantage form of this to solve this non-dimensional form. Okay, you see that this non-dimensional form, it requires an additional, math step that you do non-dimensionalization. Okay, and even after you solve the result, you got the non-dimensional form this psi and theta. And if you want to compare with experimental data, you have to scale it back to dimensional form to compare. Okay, this is tedious. But the advantage is this. The advantage is that the result you got here, okay, will be directly a function of this dimensionless parameter. Like the result you got that this non-dimensionalized of psi, non-dimensionalized form of theta will be, we don't know that there will be a function of this Prandtl number. There will be a function of this Rayleigh number. There will be this function of this angle phi. There will, there will be a function of this aspect ratio A. Okay. What does this mean? That means that the result you obtained from the non-dimensionalized form will be much more easier for you to analyze. Okay, if you write a paper, okay, if you want to analyze your calculation result, this is the step what you need to do, right? Because that you want to find that what the dimensionless parameter like affects your results, right? Okay, so this is will be the advantage of to solve the non-dimensionalized form. To solve this non-dimensionalized form, basically the result will be much more easier for you to analyze. Okay, you can conclude your result based on like you can see that okay, based from my numerical result, I can see that the temperature will increasing with the Rayleigh number, right? This is what you can see. The conclusion you can draw, rather than you can see that using dimensional quantity, which you cannot do that. Okay. So this is the advantage that you solve the non-dimensional form of the equation, and that's the reason that if you look in those software, okay, not the commercial software, but the academic people, the software developed by the academic people, because they are more, they have, this software, they develop themselves and they maintain by themselves, and they also used by those PhDs or master students. They have, and they will prefer to solve the non-dimensional form equation directly, compared with those commercial softwares. Okay, because that commercial software maybe can, they will try to design those commercial software not only can be used by PhD or master students, they also want those, just even the freshman with college students, they can use it. Okay, I'm talking. Okay, just this introducing some background why we need this non-dimensional form of equation, and why that some solver try to solve the dimensional form and some solver try to solve non-dimensional form. Both has advantage and shortcomings. Okay, so this is just some point here. Okay, so here we can using the you can just this equation is pretty straightforward to solve numerically. Okay, because that it doesn't contain too difficult terms. Okay, and you can just use using finite difference. You can do the you can use the finite difference to solve these two equations. Okay, and this is steady state, so you can either using the matrix inversion form, make it fully implicit. Okay, or you can also using some iteration way to solve this one. You guess an initial value and you're just using iteration to iterate again until you get a good result. Okay, both way are okay. Basically what I'm saying is the first one, you can just using the inverse matrix, okay? You can solve it directly, but that will be very expensive. The second way is that you can just use the iteration way to solve this equation when you write your computer code using the finite difference. And so what we found here, okay, from the non-dimensionalized form, okay, we found that there are 4 dimensionless parameter will affect the result. The Prandtl number, the Rayleigh number, the inclination angle phi, and also the aspect ratio A. Okay. So which means that both the stream function and the theta will be the results of these 4 parameters. Okay. After you got the results of the theta, you can further calculate the heat flux. Okay, on the wall AB, you can calculate the heat flux equal to minus k partial t partial x on x equal to 0, and you change the t to theta. You will and small x to big X. You get these 2 additional terms here, and you can see that this is just a definition of the Nussel number, and note that this Nussel number is defined based on the length scale width of length scale W, and also defined based on the this temperature difference Th minus Tc. Okay, so you can basically mean that after you solve the theta numerically, you can immediately get the Nussel number based on the wall AB, okay, equal to minus partial theta partial x at big X equal to 0. Similarly, okay, you can also calculate the Nussel number on the wall CD, the cold wall. Okay, it will be basically partial theta partial x and x to 1. You can also calculate the Nussel number on the 2 side wall, okay, BC and AD. That will be partial theta partial y on y equal to 0 and y equal to A. Okay, so this is some post-processing after you get your numerical result you can do to convert it to get the heat flux. And note that this heat flux you got here is the local one, because theta is a function of x and y, right? So basically, this q prime will be you got here is also a function of y. Okay, if you want to more interesting on the averaged heat flux, averaged Nussel number on the wall AB and the wall CD, you need to do an averaging. Okay, let me try to do that. So basically, you can do this q prime at W AB at wall AB. If you do average, you can do integration on the y. Okay, 0 to h q W prime AB and d of y. Okay, and so you can get that you change this y to big Y, you change this things, you can get your Nussel number average. WAB will be equal to QW average AB and times wall times width divided by K of TH minus TC. Okay. This is just same definition here, but I just changed this wall flux to this average heat flux. So basically, this is telling us that 1 over H 0 to H QW prime at wall AB times W divided by K of TH minus TOC with dy. Okay, you change this dy to smaller y to big Y, you can make it 1 over A 0 to A minus d theta d big X. Okay. This a little bit. And it big this X equal to 0. and d of big Y. Okay. So after you got your numerical solution, you can use this equation to calculate the average null number. Okay, on the wall AB. Okay, basically you just integrate additional this Y from 0 to A, and then divided by 1 over A for this quantity here. Okay. So this is the numerical way that if you want to solve this result, okay, problem. And this is the first way to study this problem. And the second way to study this problem is that we try to find some, instead of numerical solution, we try to find some analytical solution. But because the complicated of the governing equation, okay, this governing equation is you have one continuity, two momentum, and one energy equation. It's a pretty complicated problem, and we can only find the analytical solutions in very few cases, and those very limiting conditions. One example is that in the cases that when really number equal to 0, close to 0, and really number close to 0 basically means that in these cases you won't have any convection, natural convection happens actually, because that is, we know that in natural convection is that a really number like to give you that to give you the to drive flow to move actually, due to the balancing effect. And if there's no convection, that means that you just go back to our, go back to this problem here, heated from the top. Is that no flow, okay? No flow means that the problem become conduction, okay? No convection at all. And the conduction, if it become conduction, then, the temperature distribution, between the two between the heated wall, the hot wall and cold wall, it will become a linear cases, linear distribution if the side wall is said to be, no matter which type of side wall, if it's either insulated or perfectly conductive. And in that cases, the wall heat flux can be just calculated, very easily as K of, we're talking, right? If in that cases, okay, if you have this one here, if Rayleigh number equal to 0, okay, this is TH. Let me do it here. This is TH, and this is TOC, okay? And so temperature distribution, if this is TOC, it will be just a straight line, okay, across here, okay? And this gradient can be just equal to calculate at TH minus TC divided by W. And the wall heat flux at this location, will be just the K times this gradient. So it will be QW prime will be just equal to K times TH minus TC divided by W. And so if you reorganize this one, they will just showing that, you're using Q, because that you just divided the right-hand side to the left, okay? Divided the right hand from the left. You will get this null number based on this V's, based on the TH minus TC will be just equal to 1. This is one limiting cases when Rayleigh number approaching 0. And the second cases is also limiting cases, okay? We consider that first, okay, Rayleigh number going to infinity. Okay, going to infinity means that you have very strong, natural convection happens. And also that you have this inclination angle phi go to 90 degree. And 90 degree means that you have these vertical cases, right? This is TH, this is TC, okay? So that is already showing here, okay? So what in these cases, okay, because the Rayleigh number is strong, so we can see that TH is a vertical plate, heated vertical plate, and TC is a vertical cooled plate. And we can, from our previous external natural convection cases around a vertical plate, right? We can assume that you have a boundary layer, natural convective boundary layer formed for the around the left wall, and also you have a natural boundary convective boundary layer formed on the close to the wall on the right. Okay, on the left, the flow is going up because the wall is heated by the wall, and on the right, the flow is going down because it's cooled down by the wall. Okay, and between the two walls, okay, we can consider that like the free stream region for our previous external. You remember that we have this external cases, right? External natural convective flows when you have a heated wall, cooled down wall. We have this U infinity usually considered as 0. Okay. So in the region between these two boundary layers, we can consider there's no velocity. Okay. They are stagnant in the core region. Okay, which means that the velocity is no velocity here. Okay. And the temperature here based on in the steady state, okay, the temperature here can be just assumed to be the mean of the two walls. Okay, the mean value of the two walls, TH plus TC, if in the steady states, okay. And also in these cases, okay, we have this top wall and the bottom wall, the ceiling, right, and the bottom wall. We also neglect the end wall effects, okay. So if that's the cases, okay, we can just apply the Nussbaum number correlation that we obtained from this vertical plate cases before to this problem. We can just consider this T H plus TC over 2 be this T infinity, okay, and this is become TH. We can directly get the Nussbaum number around this for this boundary layer and Nussbaum number for this boundary layer. So we can know that for this problem what the heat transfer will be. And this is some recall for our previous vertical plate problem. Okay. So for our previous chapter, so this is from this is a closed results. Sorry, this is a asymptotic result to the similarity solution. Okay, and in that if we have vertical plate, we have external natural convection. So Nussbaum number divided by Grashof number to the power of 1/4 will be equal to this function of Prandtl number. Okay, this is for the local one x. And if you have plate have an overall length of h, the mean Nussbaum number on this plate h, and it will be equal to this one. Just do an integration on the x parameters from 0 to h. You can get this mean Nussbaum number correlation for this one. Okay, this is someone we can get from our previous similarity solution of this external natural convection around the vertical plate. Okay, with this two equations in mind, we try to apply these two equations to this problem. Okay, and we can have similar things. We can have this. We just copy this equation, the average one Nussbaum number h divided by Grashof h. We have a star here. Okay, I will explain why we have this star. Will be this equation. Just copy this correlation to down here. And but we have star. The reason is that the way we define this Nussbaum number, you see it here, is based on the h. Okay, remember before in our previous solution we defined all this dimension this parameter based on w, not h. And also that in these cases, okay, this h, this Nussbaum number is defined based on the temperature difference across the boundary layer. What does that mean? This is TH, okay? This is TH plus TC divided by 2 in the middle. So this Nussbaum number is defined by TH minus this TH minus TC over 2. But remember that our previous Nussbaum number, when we defined the Nussbaum number, we using TH minus TC as the temperature difference. We are not using this TH minus TH plus TC divided by 2 as the temperature difference. Okay, so that's the reason that we have a star here. Similar thing for the Grashof number, because Grashof number is also defined by this star value is defined by H and defined by the temperature difference this value rather than TH minus TC. Okay, and after you do that, you can, try to remove this star. Okay, try to change the definition of Nussbaum number from here to based on W and based on the correct temperature difference TH minus TC rather than this one. Okay, just simple substitution. Okay, you can try to define the correct Nussbaum number that we commonly use for this problem, which Nussbaum number is defined based on W, not H, the width, and also defined based on this the temperature difference TH minus TC. Okay, and divided by Grashof number will be this one. You have this aspect ratio showing up because you change H to W. And you can put this A on the right hand side, and this will be the final result looks like. Okay, and you can also change change the Grashof number to the Rayleigh number. That's times the apparent number from it. Okay, so final result, this will be the average the Nussbaum number. Okay, for this wall and for this wall, for the left wall and for the right wall, will be this equation. Okay, so this is the second case is where you can get the analytic solution. Okay, any question, guys? Let me know if you have any question.
None.
Okay. All right. So this is the exact solution, and there's one problem we need to consider a little bit more is that to talk a little bit more is that the cases when the inclination angle phi equal to 0. Okay. So this basically these cases. Okay. When you have heating from the bottom, okay, we have horizontal closures heated from the below. This problem is a little bit special because that if we consider the heated from the side, okay, when I think that heated from the side, okay, if this is TH, okay, this is TC, that you have boundary layer here, you have boundary layer here, as long as you have a small temperature difference, as long as your TH and TC is different, you will immediately forming these things to make the flow to move, okay, to move in this view, in this way. Okay, this is the cases when you have the heated from the side. But if you have the heated from the bottom, okay, so this if you have these cases, okay, you have TH here or TC here, and if you are TH and TC, okay, the hot temperature and the cold temperature, their difference is not big, okay, very small. You may not able to have any convection flow. Okay, what does that mean? That means that in these cases, the imposed temperature must exist a finite the imposed temperature difference. Okay, there is a difference. The imposed temperature difference must exceed a finite critical value before the convective flow fluid motion do occurs. Okay, does occurs. That means that if you have small difference between T and TC, you won't have any convection happens. Not like you heat it from the side. Okay, if you heat side, no matter how small it will be, you will immediately see the fluid is moving inside. But for this one, it has to be TH must be larger than TC to some extent. Okay, you will be able to see those circulating around this thing, And from the experiments, okay, this critical value can be given from this critical Rayleigh number, really defined based on W, and CR is means critical, and this Rayleigh number using the temperature difference TH minus TC to define is 1708. Okay, so that means that the Rayleigh number has to be larger than 1708 in these cases, you will able to have the convective heat transfer. If it is your Rayleigh number smaller than 1708, in these cases, you won't have any convection. And why? To explain this is very, skeptical, okay? Because the reason is this, to my understanding, okay? Because the textbook didn't say this way. And the textbook didn't explain why this. If you heat it from the side, okay? Like if you have the hot flow here, and you have the fluid like this, right? Going up. You know that if you have a fluid particle here, right? You will try to moving up, right? Along this streamline. During the whole streamline, during this whole flow path, because this streamline is parallel to this plate. So this particle will keep heated by this wall, right? Because this streamline is parallel to this plate. But if you heat it from the bottom, the T of H, you heat it from the bottom, you're going up, right? The particle going up. So that means that along this streamline, okay, the more the particle moving up, the far it from this hot heated plate. Okay, if you're going up, it will receive less and less heat from this heated wall. Okay, and it is more reluctant to going up. And I believe this is the reason why that in these horizontal cases, it has to be this temperature difference has to be large enough, like to guarantee that to this particle into fluid motion do happens, because that this streamline direction is really vertical between these two plates actually. Okay, and this is my understanding. Okay. All right. So basically means that if this Rayleigh number is smaller than this critical value, you won't have the fluid motion. Okay. Basically, it just means that you have hot temperature on the bottom, cold temperature on the top, pure conduction. The temperature gradient on this direction will be a straight line. Constant gradient will be a constant. The temperature distribution will be a streamline. Okay, this is when the Rayleigh number is smaller than critical value. When Rayleigh number is larger than critical value, if the problem is a little bit complicated. If the Rayleigh number, okay, is larger than this one, but it's still relatively small, okay, you begin to see this circulation. And we call this 2D rows, because that is circulate. If this is channel, okay, this is TH on the top and this is TC on the bottom. So it will, you see that this rotation is on this Z direction, okay. Consider this direction is Z direction. You have this rows on this D direction on these rows. But if you keep increasing the Rayleigh number, then the fluid behavior becomes that you will have this hexagonal cells actually from the bottom wall to top, just like a plume, okay, from the bottom to top of the jet, and going up, not like in this Z direction. It becomes in this X direction, okay. Flow is going from bottom to top. Flow is the X direction majorly, okay. This flow is majorly in this rotation way, okay. And it's going from bottom going up, and we call this Bernard cells, okay, this behavior, if the Rayleigh number is keep increasing. All right, so here we finish this chapter 5. This is a short chapter to talk about the internal convection. And in the beginning of the class, I forgot to talk about that, where we can see this kind of internal convection, right? What's in our general life, right? Where we can find this convection happens in enclosure. If you have if you have the windows, right? Your windows has the double glass, okay, and you have the fluid between these two pins, okay. And if you have, you have the room temperature is hot, the outside temperature is cold, the air, okay, between these two, between the two glasses of the window, they can become this natural convection inside the enclosure. Okay, and other things like if you have that solar panel, okay, solar collector, solar energy collector, you know that you have between that collector plate and you have on the top of the solar collector plate, you will also have a glass to protect it, right? And you will have the gap between the collector plate and the glass plate. You will also have air in the middle, okay? And that will be you will see the natural convection, internal natural convection there. Okay, and also you can see some other cases like if you have computer case, okay, you have motherboard, and the motherboard you can consider the hot wall, and the computer case if you have no case fans, no CPU fans, those kinds of things, you can consider this your closed environments. You can have those natural convections happen there. Okay, this is where you have possibly you can see the internal natural convections actually. Any question? Because I will finish this chapter.
No.
Okay. All right. So this will be now we will move into the next topic. Okay. So we finish the topic of the natural convection. Okay. We talked about the internal, external, and internal natural convection already. So now we are moving to the next topic. Next topic is turbulence. This is the last topic of this class. All our previous lectures, okay, when we're talking about the force convection, internal, external, or internal. External means the flow over flat plate, those kinds of things, and internal means that the flow inside the pipes. We only consider, the flow is laminar. Okay. Same thing. Okay. When we talk about the natural convection, we talk about the external one, flow around natural convection around the vertical plate, and the internal one. For this one, we're talking about here, natural convection inside the enclosure. We all consider that the flow problem is laminar. We didn't consider the effects of turbulence. Okay, and the turbulence that when the Reynolds number is big, okay, for the force convection, okay, we know that the flow will eventually transit from the laminar flow to the turbulence flow, and similar things, okay, for the natural convection. If this reading number become big, okay, when reading number is small, you can consider it's laminar natural convection, and when reading number is big, the natural convection can also transit from the laminar cases to the turbulent cases, okay, turbulent flow. And when you have turbulence flow, okay, the first thing you need to know that is that all the governing equation we have here, this, for example, for this governing equation, uxvy, this term, and this momentum equation, conservation momentum and conservation of energy equation, those equations will not be in this form anymore. Okay, this is the first thing you need to know. So we will have a new equation to solve, okay, for the turbulence one. And the second thing that you need to know that because this class is focused on the heat transfer, right? And if you're looking at this Nussel number distribution, okay, sorry, Nussel number correlations, like we can just using this, where is it? Oh, let me get this natural case. Let me using these cases, okay? You can see this Nussel number will be proportional to the Rayleigh number, right? That means that usually speaking that the more you increase the flow velocity, if like you increase the Reynolds number for the force convection, or you increase the Rayleigh number, in the natural convection, you're probably more likely to increase the heat transfer. Okay, this is common sense, right? That's why is that in the convection we want more fluid, we want the fluid to moving faster, right? If you have a fan, okay, to blow the wind to me, if the wind speed the speed is higher, I will feel cold, right? If it's slow, I won't feel that cold actually, which means that we know that increasing the velocity usually increase the heat transfer rate. Okay, this is similar to the things to the turbulence, right? Because we know that for the turbulence, we will have higher Reynolds number and higher Rayleigh number for natural convection, or higher Reynolds number for forced convection. So you can expect that for the turbulence convection, no matter it is forced convection or natural convection, their heat transfer rate will be much more than will be bigger, okay, than the laminar cases, corresponding laminar cases. Okay, I explain this from the view that because velocity is high, we may feel it's more energy will be heat transfer, bring away, okay, something like that. This is one reason, okay. Another reason we will explain later, okay, because the special things of the turbulence, okay. Okay, let me go to open that. Chapter 6. Okay, so chapter 6 will be a short introduction of the turbulence flow, okay? Turbulent flow. And turbulent flow is a very difficult topic. Very, very difficult, very, very challenging, okay? And because I'm a CFD guy, okay? CFD people. So it's like, all those laminar problem, okay? In this day, nobody studied them, right? Because that it's very simple to solve from the Navier-Stokes, and you can solve the problem, even with the complicated geometry very quickly for the laminar flow. But for the turbulent flow, it always give you more trouble, and also that the theory behind the turbulence flow is also very challenging, because that it will involve many statistical behavior in the turbulence flows. Okay, and so the first thing we are talking about that is that the statistical description of the turbulence. Okay. So what's the turbulence? How do we using the math? Okay, using the math to correct, describe the turbulence problem. Okay, and turbulence basically means that it's not a constant thing, right? It will like if you, here you will have a temperature around the point, okay, and with the time, maybe it will fluctuating with the time, okay, and in the turbulence flow or fluid location, or one location in that fluid. And one thing we can do is that if this flow is stationary flow, okay, stationary flow means that the flow is approaching to steady state already, okay, and if we can do the time averaging. Okay, the time averaging means that you can calculate the mean value of U, velocity, VW, or P, pressure, temperature, through a time interval between 0 to T on this small p, on this instantaneous value, U, VT. This U, okay, without any bar or this prime means the instantaneous value. And the result will be U or U bar. Okay? This U bar means U average, means the mean velocity will average it over time interval. Okay, and you can definitely these two will not be same. Okay, instantaneous and average one. The difference between the instantaneous and average one will be this U prime. We call it the fluctuating velocity, and this fluctuating is purely due to the statistical behavior of the turbulence. Okay, it's not due to the transient effect. Okay, it's not like because the flow is still developing. No, we already assume that the flow is approaching to the steady state. Okay, and this U prime is only because of this statistical behavior. And if you do averaging on this fluctuating quantities, it will become 0. Okay, the mean of this fluctuating quantity will be 0. And this time is has to be is need to be very large. Okay, if you want to get an accurate result of U mean. And in theoretically, it should go to infinity. Okay, when you do the averaging, like this time can go to infinity. So you can get the average value U bar, W bar, T bar, V bar, and T bar. Okay, this is one way, you can describe the turbulence that you represent the instantaneous quantity, okay, into two parts. One is the mean part, and is the fluctuating part. Okay, but this is what we called time averaging. And you need to know that this time averaging is only working for the steady state flow. Okay, if the flow is still developing, you won't be able to using time averaging. Okay, because when you do time averaging, the average this average value U bar is also changing with the time, and this U prime you got is not only contains this random effects of the turbulence, but also including the involution of the time involution of the fluid behavior, of the unsteady flows. So this is the time averaging. As I said, it's only working for the steady state flow. Okay? But if for the unsteady state flows, how we can do, using the math to describe this turbulence quantity. That is the second averaging. It's called the ensemble averaging. Okay, it can working for the non-steady state flows. Again, okay, it still be two parts. So for instantaneous result, it will be the averaged result, averaged part, and the fluctuating part. But the average part is not calculated by the integration of time anymore. It's based on your realizations. Okay, number of sampling realizations. Basically means that you do is unsteady state, right? But you do this unsteady state flows many times. This is the first time you do experiments for this unsteady state problem between some zero, between some for some t time range. Okay, and then you do the second time, do the third time. Then you do average between these realizations. T equal to 1, this T equal to 1, T equal to 2, T equal to n. You get the average averages on all these realizations. Okay, on this direction, not on this direction. Okay, this is the time direction, and this is so-called the ensemble average. Okay, and basically you just do average of all these ensembles samples actually, and this n theoretically should go to infinity so that you can reach the theoretical, mean value actually. Okay, so this is so we call the ensemble averaging, which you can use it for the non-steady state problems. Okay, and we have these two types of averaging: time averaging for steady state, ensemble averaging for unsteady state. And both of them, you're just doing the same thing, right? Try to separate the instantaneous quantities into averaged quantities plus fluctuating quantities. And these two methods is usually referred as the Reynolds averaging. The reason is that because this guy Reno, okay, he first, developed this theory that the instantaneous can be divided by the two parts. So that's the reason we call this two averaging technique. We call this Reynolds average. Okay. So this is the first thing we need to know for the turbulence. And there are some, more things we can talk about this averaging things. Okay. This, Reynolds averaging basically is what I say, runs, right? It's usually using only for runs method. Okay. This we call it averaging. Averaging. What is runs? Runs is standard, it means that Reynolds averaged the Navier-Stokes equation. Reynolds average analysis. We will go to the equation there. Okay. Basically, that means that the Navier-Stokes equation, the way we doing Navier-Stokes equation is using this Reynolds, using the averaging averaging behaviors, averaging techniques that we have here. Okay, either time averaging or ensemble averaging. So this is the one way we study the turbulence, right? And if you, maybe some of you already know, right? There are three major ways we can study the turbulence. Runs is the Reynolds average, the Navier-Stokes is the most simple way. Okay? And we also have the large ID simulation, LES. Okay. And in the large ID simulation, we do not do the average. Okay. We do not do the averaging. We do the so-called filtering. Okay. I will explain a little bit for you what the filtering means. Okay. And the last one, we'll have the DNS, direct numerical simulation. Okay, this is the three major numerical techniques we have to solve the turbulence problems. Okay, we will go more for runs in this class. Okay, and you already know what the averaging means. Averaging, we can do average on time. Okay, average on this ensembles. And what is the LES? We call it filtering. Filtering means it's not averaging. Okay, filtering means you can consider that averaging. Okay, average on time, right? On time. And ensembles is also like some samples on the temporal space. Okay. Filtering is actually, you can consider that it's something like smoothing, or some kind of, you can also consider it some kind of averaging. Okay, but it's not really averaging. It's a kind of some smoothing. Okay, averaging on spatial. Okay, on the spatial scheme, spatial space. Okay, this is a runs you average on the time, right? On the temporal scheme, temporal space. And filtering in the LES is you try to do the averaging on the space, on the X, Y, Z, this kind of thing. What does this mean? This means that first we need to know that a turbulence series, which is called the energy cascade. Okay. And in turbulence, we have so many vortices, right? Usually we call it the eddies. Okay. This is too big. We call it eddies. Small, okay. We call it eddies. Okay. And in turbulence, it's eddies, okay. The way the turbulence is working is that we have a large scale, large eddies, okay. Their length is big, okay. This is big. And we also have this small eddies. And the energy is transferred from large eddy to smaller eddy, okay. This energy, the kinetic energy, okay. The energy I'm talking is kinetic energy, the energy from the velocity, okay. It will transfer from the large eddy to smaller size eddy, and smaller size eddy to this smaller size eddy, smaller size eddy, until to this eddy, which has a minimum mass, minimum size, okay. And if you're familiar with the turbulence yourself, this is the Kolmogorov scale actually. And what does it mean? This means that looking about the Reynolds number, right? No, forget about Reynolds number, okay. And when the when we have this turbulence, right? Actually, the energy is transfer the kinetic energy, right? This is maybe u square. Okay, consider this velocity. Okay, from the smaller energy to the end scale, and when they transfer the energy, okay, some energy is going to temperature because of viscous effect, right? You know that we have this mu in the Navier-Stokes, right? So this viscous effect, this mu, basically this mu viscosity, fluid viscosity, basically this mu is just like a friction, right? If you can transfer the thermal, can transfer the kinetic energy to the thermal energy, and so basically to the temperature, to the temperature, okay, to the thermal, and to the smallest eddy, and this smallest eddy actually will transfer everything to the temperature, to the thermal, okay, kinetic energy. Okay, so all kinetic energy will eventually transfer to the temperature if we can pass all this way down. Okay. Okay. So what the RES means? RES means that we only simulate the problem for these large eddies, like we draw a line here. Okay, we just study the fluid motion for these large eddies, and for this smaller one, we just do not study it. We just using some empirical equations, models to model it. This is RES, and this is what the filtering means. Filtering means that you set a filter here. The eddy is larger than this filter, we solve it. The eddy is smaller than this filter, we model it. Okay, so this is what the filter means, and this is what I mean that it's basically it's working on the spatial space actually. Okay, now what's the DNS? The DNS directly numerical simulation. The DNS basically is that you just try to solve all the scales. Okay, you try to resolve all the large eddy until the smallest eddy, and the smallest eddy is the Kolmogorov scale. Okay, Kolmogorov scale. Okay, Kolmogorov scale. This is smallest eddy. Basically, what that means is that if you using finite difference method, your grid point, okay, your grid point in your finite difference has to be as smaller as this scale here, your grid point, and then you can just solve the the Navier-Stokes equation we have in our chapter 2 directly without involving any fluctuation terms or any turbulence modeling in the DNS. You can just solve it directly, okay? And this basically DNS actually resolve all scales, okay? And RES is try to resolve most scales, okay? And the runs, people are thinking about it. Is thinking that some people is saying that it is only resolve large scales, because in the runs that when you do this averaging, it's like this is more prominent, right? When you do the averaging, this is large eddy, okay. So that's the difference between these three, okay. That's why it's like the runs is the most easy way to do, but result is not accurate. And RES is a little bit more difficult, but result is better than runs. But and the DNS is the most accurate one, but it will be very expensive to do. And in these days, okay, more and more people doing DNS direct numerical simulation is because it's supercomputers. Okay, we have very supercomputers like you can using like 10,000 CPUs. Okay, 10,000 terabyte memories. So that you can have very fun that great skills in our finite difference or finite element method. Then you can resolve it. So more and more people doing DNS actually. Okay, but this is the most simple one, and we'll talk about the runs in this lecture. And for the other two, you will learn more for your turbulence class. Okay, I think it's 512, MEC 512. I think for the introduction to turbulence section. So these are some background for this three method. And you know, you need to know that it's a class in this, what we are talking right now for this averaging is only for the first method, okay? Only for the rest, not for the RES and DNS. Okay, so we need to divide derive the Reynolds average Navier-Stokes equation. Okay, and the way to derive it is very simple. Okay, you know that for example, if you have this momentum equation, instantaneous momentum equation will be this one, same as before. U partial y equal to minus partial p of partial x for 2D. Okay, that's using 2D answer, plus nu partial square u partial x square partial square u partial y square, right? So this will be instantaneous governing equation for the x momentum. Is similar as what we derived in the chapter 2. Okay. Now you just need to bring this u become u bar plus u prime for this one, and partial u bar plus u prime, right? And partial x plus, you know, v bar plus v prime, and partial v bar plus v prime, partial x, you know, just separate this UVP, you know, to both, you know, average value plus the fluctuating value, you know, plus mu by partial square u bar partial u prime partial x square plus partial square u bar partial u prime, oh, divided by partial y square. Okay. After doing this, okay, you do averaging on the both side. You do another averaging on the left and right hand side. This bar on the top, okay, on the both sides. And you know, because that we know that this u prime will become to 0, right? So some term will going gone, okay, and some other term will keep, okay, and this will be your final result on the left hand side. You know, the continuity equation is still the same, almost is the same form as the instantaneous form. Okay, you know, UVW just replace the instantaneous UVW to this average UVW. Okay, but for these three momentum equation, the x momentum equation, y momentum equation, z momentum. So this is I'm using 3D cases. Actually, I assume is incompressible, means that density is constant. Density is constant, and also constant fluid properties means that you know, this mu I can put, and we can take it out of this derivative. Okay, and all similar things for the alpha. And the steady state means that I neglect the transient term for the Cartesian coordinates. Okay, for after you do this averaging, okay, you will see that and from here, okay, this is still the same form as the instantaneous equation. Same form with integration. We have the convection term, we have the pressure term, we have the viscous term. But we will have an additional term here. Okay, and this additional term is the average of u prime times u prime, average of u prime times v prime, average of u prime times w prime. This equal to 0. Okay, u prime equal to average of u prime equal to 0, right? But this average u prime is not equal to 0. Okay, because this means this averaging means the correlation between these two. They are correlated, positive correlated. Okay, if you take the statistical class before, so you won't be able to be 0 for these random quantities. Okay, and this additional terms here. Okay, this additional terms here with this bar term for these random correlation terms, we call this Reynolds stress. Okay. I do not have space here, so maybe let me remove this. Let me just remove this, all this. Okay, so all this partial ui prime, ug prime over partial xg, okay, and the ig can be 1, 2, 3, okay. This is the instant notation, okay. Tensor notation, sorry. All this is called This bar is not here. This bar here. Okay. This is called the Reynolds stress. Okay. Why we call it stress? Because that it is on the right hand side. Actually, it behaves similar to this viscous stress. This is the viscous terms, right? Viscous stress, like because you have a negative sign here. All this Reynolds stress is also helping to, like the viscous, try to convert the kinetic energy to the thermal energy. We know that as we talked before, right? Viscous that convert this kinetic energy to the temperature thermal energy, right? And this is also negative term. Is also negative means destruction term. Okay, it also try to reduce the kinetic energy, but convert it to the thermal energy. Okay, so we call it spectrum. And these terms, this is the additional terms when we have this averaged Reynolds average navigable equation compared with the instantaneous equation. And this term, okay, can be dominated. Okay, if this term is very small, maybe we can neglect it. Okay, but in the many cases, okay, they can be dominated. Okay, in turbulence flows. So this Reynolds stress is very important to study. And similarly, we have Reynolds stress, Reynolds term here, Reynolds stress term for all momentum equation. And for the energy equation, we will also have these additional terms between the correlations of the velocity fluctuation and temperature fluctuation between the correlation. Okay. And one thing, this term is important, but this term is also very brings the challenges. Okay. The reason is that how we know these values, because we do not know that what the U prime correlation, U prime, V prime averaging, U prime, W prime averaging, U prime, T prime. We do not know these terms. Okay. So they are all unknown terms. Okay. They are all the things. So, which means that before, okay, for the instantaneous Navier-Stokes, we only have UVWPT. We only have 4 UVWPT. We only have these 5 unknowns, and then we have these 5 governing equations. We can solve it. But now, after we do the averaging, okay, this U bar, V bar, W bar, P bar, T bar, this T average value, U average, V average, W average, P average, T average. We do not know. We still do not know. But now we have this additional unknowns. We have this unknown, this unknown, this unknown, this unknown, this unknown, this unknown, this one, this one, this one, this one, this one. All these Reynolds stress terms is also unknowns. Okay, we have more unknowns than available governing equations we have. And that means that we need to have more governing equations, right? And so we need more equations to resolve this term. Resolve these terms. Okay, we need more equations to resolve these terms. And these equations, this is the equation we need to add, okay? Because we already contain all the conservation laws, okay? We cannot find more conservation laws for these terms, actually. We have the momentum, we have the mass, we have the energy, okay? What else conservation law we can add it? Nothing, okay? And which means that this equation we added won't able to come in from physical behavior, okay? We won't come from this conservation law. And that's what the meaning of this equation we are added is not the real conservation equation, but rather than models. And this is called the turbulence models. Turbulent models. Okay, we need to find turbulent models for all to add additional equations to resolve this additional unknown terms. Okay. That's why we always see hear about that turbulence model, because we have this additional term to solve. Okay, this is one thing. And another thing, important thing is that you need to be looking at this negative sign here. Okay, as I told you, negative sign means that you just remove the energy from the kinetic field, kinetic energy, because that negative sign means that okay, you can see that this negative sign, okay, means that dissipate. These terms help to dissipate kinetic energy to thermal energy. Okay. And another thing is that you need to know that where this term is coming from. Where this non-dimensionalized term coming from? All this all this Reynolds stress term is coming from this from these terms here, from the convection terms. Okay, it's not these terms u prime is not derived from the pressure term of the instantaneous equation or viscous term of the instantaneous. It's all coming from the convective term of that instantaneous equation. And okay, so all these terms, okay, originated, okay, are originated from the nonlinear, okay, convective terms. So this nonlinear is very important, okay? Nonlinear, you see that this convective term, you have u times u, right? You have v times u, you have w times u. So inside this Navier-Stokes equation, the convective term, okay, is usually only the term has nonlinearity, okay, nonlinearity. And this u prime is just because it's really coming from this u times u, okay? If it is not u times u, it's a constant times u, we won't able to have these terms, okay? So, and what I mean is that here is that you need to know that, this additional Reynolds stress term is raised because the nonlinear behavior of the convective term, okay? That's making it very difficult to solve. If it's linear, we can solve it immediately, actually. Okay, so this is equations. And then now we are talking about the turbulence modeling, right? How we can model the turbulence for these terms. The most, no, let me, so this is a summary, okay? This is the unknowns we want to solve: U bar, V bar, W bar, P bar, T bar, and this additional 9. In this 3D problem, we have this additional 9 Reynolds stress. We need to find the equations. We need to do the turbulence model for each stress terms so that we can solve it. How we can do that? Okay. The easiest way to do the turbulence modeling is that if we can find that this terms, okay. If we can find that if we can find all these terms can be a function of their average term can be function of u, v, w, p, t, okay. So if we can find a term that is a function of this average terms, because this average term is what we want to solve, right? Because we are interested in that the mean flow velocity. We are interested in, we want to know what the mean pressure and the mean temperature of the flow field. Okay. So if we can model this Reynolds stress terms as a function, turbulence stress terms in terms of averaged values, then that will be good things, okay? That means that we reduce the number of unknowns, so that we have 5 equations and only 5 unknowns here to solve, okay? So based on this, okay, the most simple way to to do the turbulence modeling is the so-called mixing length theory, I won't give you too many details of the, how this theory is developed. What of, physics is in the standby to use actually. But I just give you the final result. Okay. So in this mixing length theory, okay, like this term U prime V prime, you're seeing that this term can be approximated by mu t times partial U average value of U on the y direction gradient on the y direction partial y. And this nu t is so-called the ID viscosity. So nu t is different with nu. Okay, nu is just the viscosity, kinetic viscosity. Okay, it's bulk viscosity. Okay, in the mean flow, and this mu t is called the ID viscosity, which means that it is the viscosity for the turbulence field actually. And if you look in this equation directly, okay, this equation basically just using the same analogy. Let me write it more clear. Okay. Same analogy to transport loss. Okay. Okay. As I told you, it's this renal stress, right? They can transfer they can do additional diffusion. Okay, some viscous diffusion, like to transfer the kinetic energy to thermal energy, which means that they have the same role as those mu terms. Okay, so they are actually is a transport effect to transport the energy from the kinetic to thermal. Okay, and what this transport means, the transport loss. What's the usually transport loss we have? We can have the Ficker's law. This is the law to transfer, like if you have the concentration, right? Concentration from the high concentration species to the low concentration species, right? We have this G equal to minus D diffusivity equal to dC of dx, right? You see that what I say, the concentration transport flux will be equal to minus D is diffusivity times their derivative, basically the constant time derivative. So for temperature, we have the Fourier's law, right? For conduction. So we have that Q prime prime equal to minus K dt dx, right? We know that, the thermal heat flux for conduction is like a constant times the temperature gradient. Okay. And we also have the drag, right? We know that tau W equal to, minus D du dx dy, okay, or dx, whatever, okay. It's like the drag force is also a constant times the gradient. These are all transport loss, okay. And same thing because it is also transport process. So we can also assume that is at a constant times the gradient. And the gradient will be the driving force for this transport effect, transport process. Like the energy, right? We know that is the temperature difference derived is the driving force, the energy heat transfer. And also we know that this is the concentration difference is the driving force for this diffusion, species diffusion. Okay. And also we know that this is the temperature velocity difference is the driving force for this for the drag effect. And so that is here we can see that okay, we can constant times gradient to estimate to analog to this similar transport loss. This is where this theory is developed from. Okay, and this and also okay, we need to prove that this will be the driving force for this term. Okay, it can be approved, but I won't go to that details because you can know that it's a mean velocity gradient. The velocity gradient can bring that turbulence effects actually. Okay, and this mu t constant, unknown. We do not know here yet, but we know that it should be some constant here. We call this the ID viscosity. Okay. And also this mixing length theory, they are also showing that this mu t here, the ID viscosity, this value will be approximated to some length scale Lm square, and this Lm is called mixing length. It's the length of the largest ID in the turbulence field. Okay, so we assume that is this largest ID, its length can define this can be used as a length scale to define this character mu t here, and if you have this mu t, if you do the dimensional analysis, this ID viscosity will have the same unit as the if you or not. Yeah, if you have the same unit as the kinetic viscosity. So you have length scale here, you also need the velocity gradient scale, okay? And you can this from this theory, you can prove that this nu t is also approximate to this length scale square times this partial u partial y magnitude. Okay, so if you put these two together, you can see that okay, this Reynolds stress u v prime will be equal to L m square times partial v partial y magnitude times partial u partial y. Okay, and similarly for the temperature fluctuating correlated term to the velocity fluctuating, you know, we can have an additional, because that is the length scale. Okay, this Lm for the velocity field and the Lm for this correlation, it may be not same. Okay, so we just times an additional c here, and no c here, to be Lm square and times the partial v partial y, but this one you become 2t partial y here to approximate. So this is the turbulence modeling we are doing here. You know, this correspondingly you can write for the other 5 terms for the velocity correlations. Okay, and also that between velocity and temperature correlations you can using this one. Okay, and we do not know what Lm it is now, and we do not know what c value will be. But generally speaking, that c is you can be, because that c is for this temperature correlation, right? Is for the thermal one, and this is for the momentum one. And we can see even using this one divided by this one, using thermal divided by momentum, basically it's using alpha divided by mu. It's like some Prandtl number. Okay, so you can see that you know, people are really seeing that this 1 over c is related to a so-called turbulent Prandtl number. Okay, so now the question is that if we want to using this modeling, okay, we have 2 unknowns. Okay, we do not know what is Lm, and we do not know what is the Prandtl number, turbulence Prandtl number. So if we can find these 2 values for your problem, you can just using this to estimate all these unknown terms. Okay, so in general speaking, okay, that makes the cases more, the equation more concise, okay, more clean. So in this mixing layer theory, okay, all the velocity correlation can be equal to mu t times this one. This is a deformation tensor, okay, and where nu t can be equal to this one, okay, and for the temperature part, okay, it can be related to alpha t times partial t partial xi, and the alpha t is determined by nu t, or nu t divided by turbulence Prandtl number. Okay, going to the previous slide, this I saying that this is 2 unknown function, 2 unknown parameter, but if we group the equation in this way, and this will be 2 mu t and Prandtl number t. Okay, so ID viscosity and ID viscosity and turbulent Prandtl number is the one we are looking for. Okay, all right. So turbulence modeling based on the mixing length theory basically is becoming that parameterizing. Okay, parameterizing means that we need to find that what's the value of now this one nu t and the Prandtl number for different types of problems based on the experimental data. What do you mean? What do I mean is that we can do an experimental data on some turbulence problem, right? We can measure that, try to measure that for that problem, what the new T will be and what the Prandtl T will be. And after we find those parameters, you know, in the future, if we want to calculate the flow problems similar to that experimental problems, you know, we can just using CFD, using this new T and the turbulence Prandtl number, and using this mixing length theory, you know, using this mixing length theory here, you know, to close those unclosed terms. Okay, this is the most simple turbulence models. Okay, the mixing length theory. All right. Any question?
No.
Okay, that's good. And this is a simple one, but this problem, this theory has some issue. The most issue is that, you know, after this theory is developed, when researchers, okay, many researchers try to find this what's of these two values, nu T and the Prandtl number T. They may find that nu T and the Prandtl number T for turbulence flow over a flat plate. They may find this nu T and the Prandtl number T for the turbulence flow inside the pipes. But what they found is that this nu T and Prandtl T, the value for these cases and for the cases, they are very different. Okay, that means that it's not possible you find a constant this nu T and Prandtl number T turbulence with ID viscosity and also this turbulent Prandtl number for all cases, for all cases, for all fluid problems. For each problem, they will have different value. So this makes this model not very useful anymore. Okay, because that you know, I have some values derived from some experimental data, but these values I won't able to use it for many other problems. So this makes this problem really not good. Okay, and that's why it's a more advanced model, you know, is developed. Okay, for the runs. Okay, this runs method, Reynolds average, Navier-Stokes equation, advanced turbulence model. You know, many of you maybe already heard about, right? K epsilon model, K omega model, and these two equation model, and also some other one equation model like Armara's model, and even some more equations, three equation model, and so on. Okay. So I just give you quickly an example that what two equation K epsilon model. Okay. I'll tell you that what does this mean? Okay, how it works actually. You know, I just neglect that. I won't give you that how this model is derived. Okay, you know how it was derived from those statistical theory, you know, from those kind of things. But I just give you the result and how you can use this equation directly. This is a K epsilon model, and first you need to know what is K and what is epsilon, right? K is called turbulence kinetic energy, and in the shortcut this is called TKE. Okay. And so it will be U prime square bar, okay, plus V prime square bar plus W prime square bar. This bar is over this square, okay. You do the square first, and then you do average. Okay. And divided by 2. So this is like a kinetic energy for the turbulence quantities. And you can derive the conservation for this turbulence kinetic energy. And you will have these terms, UG, average value, partial K, partial XG, nu T, okay. This is something I do not know. And UI, XG, UG, XI, UI, XG, all this U is average value, is good actually. But it is the unknown we want to solve. And this is nu T and another constant sigma K, and partial K, partial XG, and minus epsilon. And here is where the epsilon is we have, okay, in this equation. And the epsilon is called the rate of dissipation of K, okay. So basically it's the dissipation rate of this TKE. And we also have an equation for the epsilon. And epsilon is similar to K, okay, terms. We have this convectivity term for the epsilon. We have some constant times this production term. This is how the production of the K. Okay, it's because it's positive, like how the K, turbulence and kinetic energy is we have positive K value created in this term. And this is a positive productive term for the epsilon. And this is viscous transport term for the K and epsilon. And also we have this dissipation term for the epsilon. Okay, so we have these two terms, and we also have this some unknown constant, right? This we do not know this sigma K here. We do not know this C1 epsilon, C2 epsilon. We do not know this sigma epsilon, and all this constant is given, okay, with this equation, and this constant is derived by is obtained from the experiments, okay, many turbulence experiments, to find this is the best values for this equation. And also after you got the K and epsilon solved, you can using this correlation to calculate the nu T. Okay, and so after you got the nu T, okay, and also remember that this nu T is also showing inside this equation, but it's just coupling inside. Okay, so it doesn't matter if you solve it iteratively. Okay, so after you got the epsilon and K, you can use this one to calculate the ID viscosity. And after you get the ID viscosity, you go back using this one to modeling this term. And also you can using this term equation to calculate the alpha T. And the Prandtl T, okay. In our usually people just assume this Prandtl number of T as a constant, like 0.9 or point something. Okay, I think in some researches, some papers I read, and some work I did before, just assuming it's as a constant you can. Okay, so what I mean is that if you want to use the K epsilon equation, okay, basically is that what you need to do is that you will have the following unknown. Okay, you will have U unknown, V unknown, P unknown. Oh, sorry. You will also have W unknown, P unknown, T unknown, K unknown, and epsilon unknown. Okay. You will have 5 unknowns, but you will have 7 equations. You will have that Navier-Stokes Rance equation, 5 conservation equations. 1 continuity, 3 momentum, 1 energy, and you will also have these 2 additional K epsilon equation. After you solve this K epsilon equation, you can calculate the mu T, right? After you calculate mu T based on this constant Prandtl number of turbulence Prandtl number, you can calculate this all. You can model using this mixing line theory. You can, model all these Reynolds stress terms here. So which means that you can solve all the problems. So this is how you can, using this K epsilon model to solve the Rance problem. Any question?
No.
Okay, I think today we're going very fast actually, because today there is a lot of descriptive theory, okay, and so we just need to talk. So it's now we go to the last slide, and the last slide is your knowledge about the turbulence around the wall. Okay. Okay. So let me think about it. If you have a fluid particle, right? Consider this is x direction, and this is y direction, right? And we know that they have the u average velocity here, v average velocity here for this particle, and also you know that we will have u prime and v prime here, right? This for this particle. This is average velocity. This is fluctuating velocity. Yeah. Okay. It's okay for this particle, moving inside a fluid. But what happens if this particle is moving close to a wall? If we have a wall here, and this particle is very close to it, okay, in a region very, very close to this wall, what does it mean? which means that in these cases, okay, if this is still y direction and this is still x direction, okay, and on the v direction is fine, okay, you will still have a v averaging and a v prime things here, right? But on the x direction, this u averaging will go to 0, right? As because it's very close to the wall in the boundary layer due to viscous effect. And the u prime, this fluctuating, not only the averaging will become down, u prime is also going to 0 because that you have a physical obstacle here. That's to stop this particle to moving randomly on the x direction. So u prime is also going to 0. Okay. So what that means? That means that when the particle, okay, is close to a wall, okay, and also, sorry, I make a mistake here. Also, because the v velocity is also become to 0 at the wall, okay, there's no, we do not have a penetration, okay, of the velocity through the wall. So v velocity also becomes 0. And because the averaging v velocity becomes 0, v prime is also going to 0, okay. So that means that in this particle close to the wall, in a region, okay, in the region very close to the wall, the turbulence stress, okay, all this u prime, v prime term, okay, all these terms, and the turbulence heat transfer term, all these u prime, t prime terms will become neglectable, okay, in the region very close to the wall because viscous effect is very strong, okay, much more stronger than this dissipation term. And so, and in this region, okay, we really usually call the sublayer, you know, consider a small layer. You know, if we have a wall here, and you know, if it is the y direction, we can see that at some location, you know, in this region here, you know, if the fluid inside this small region close to the wall, okay, we can consider that in this region, there's no turbulence effect, only the laminar flow, okay, no turbulence effect at all, only the laminar flow. Although maybe outside is turbulence here, turbulence here, turbulence, but even close to the wall, then we will not be able to have any turbulence effect, only the laminar one. And in this region, we can call this region is termed as the sublayer. Okay, called the sublayer close to the wall. And if it's close to the wall, okay, we can calculate the you know, both the wall wall what I say, friction force and wall heat transfer rate by using this drag law and this Fourier's law. Alpha times rho Cp is k, okay. And also we can assume that because it's laminar, right? So it's the thing changing here. The region is very small. We can just assume that the changing of velocity and the changing of the temperature inside this region is just linear, okay. The changing this du dy, dt dy can be considered as some, you know, because here is 0, right? And here is u, right? U bar here, right? Because at the end it will be, and here will be t wall, and here will be t bar. Okay. The changing from t u0 to u is linear, and from the changing from temperature from tw to the t bar is also linear. Okay. So now you can change this du dy just equal to, you know, u divided by u bar divided by y, and you're changing this t bar divided by y become tw minus t tw minus t divided by y. Okay, this will be, and after you do that in this sublayer, okay, this is the so we can see that okay, this will be the, you know, if the flow in the sublayer, okay, at any location y, we can calculate the u velocity and t mean velocity based on this correlation if we know the we know the we know the friction force and heat transfer rate. Okay, and again we can introduce in this so-called this dimensionless parameter. First, we can calculate u star equal to tau w divided by rho over square root, and this u star is called friction velocity. And after we get U star, we can define a dimensionless velocity U plus, which will be this U bar averaged bulk velocity divided by this friction velocity U star, and we continue U plus. And similarly, you can define this Y dimensionless Y coordinate. Y plus will be equal to Y times this U star divided by mu. This is mu, okay? Not V, okay, mu. And after doing that, okay, this correlation will be changed to this one, U plus equal to Y plus, okay? And basically what I'm saying is that after you do this non-normalization, we can see that in sublayer, you know, the velocity is linear along the Y direction. U plus is just equal to Y plus. All right, okay. So people are doing this, okay? Based on the theory, if you have a wall, okay, if you have a wall here, and if you have this y-axis as y plus, okay, people saying, usually people saying that when y plus between 0 and 5, okay, assume here is 5, okay, y plus equal to 5, and this region, under this region, okay, we call this inner region or sublayer, okay, it's the same thing we called the sublayer before. And in the inner region, the u velocity, u is just a straight line, okay, like a u plus equals to y plus. And also from the experimental, okay, people find that not from experimental, actually, it's derived from some theory, okay, they call the log velocity region, okay, and I won't give you details actually, but you can, if you take the physics class, you can knowing that, okay. Between y plus 5, y plus you can go to 5 to 30, okay. Let's see if we have 30 here. So this is 30 in this region. They call this region buffer region, okay. And in the buffer region, the velocity distribution is not a u plus is not a linear to y plus, okay. It will become a log correlation if you use something like this, these things, a log way to change, okay, something like this between this one, if we see this. And after, and this is the result, u plus equal to 5 times the log y plus minus 3.05, okay. And if y plus is larger than 30, this region here, this we call it the outer region. Okay. So this outer region is more divided by the Rand's Navier-Stokes equations, okay, different on based on different problems. So basically that means that this is region where turbulence effect maybe becomes strong. Okay. And in this two region, you know, in this region we can totally assume it's laminar, okay. And in this region you can consider like some transition region in the log law, okay, where the turbulence is not that strong. But in the outside region, you can consider that the turbulence can be strong. Okay, depend on the mean Reynolds number for Reynolds number. Okay, so this will tell you that you know how the wall, okay, flow near the wall, the effects of turbulence will be affected. Okay, so this is some other theory we need to know for our future study of the turbulence convection. Okay, so this is the last one I have for this chapter 6. So we finish this chapter. And what's the remaining? Okay, we have 2 classes left, right? So basically the remaining class is that 2 classes will going to study the turbulence convection, you know, for the previous problem we studied before. What's the turbulence convection effects for the external force convection, like that boundary layer theory? What the turbulence boundary layer theory will be, right, for that one. And also that we will see for the internal internal force convection, like for the flow inside the pipes, through the pipes, circular pipes. If the flow is turbulence, what the Nussbaum number will be, right? What the pressure drop will be. And also for the natural convection, if it's external natural convection, flow close to a vertical plate, if the flow becomes turbulence, how the Nussbaum number is changed. And also for the natural convection, internal natural convection, like the convection, free convection, and natural convection inside the enclosure, that enclosure, the first part of our class, today's class, how the turbulence will affect those Nussbaum number behavior. Okay, this is the things we are going to for the next 2 classes, and then we'll finish this semester for this class. For turbulence, okay, 2 things we want to find, okay, 2 questions we want to ask. The first question is that when laminar go to turbulence, we want to know that at what point time laminar can become turbulence. As I already told you that for the force convection is the Reynolds number determines this, right? So basically means that for the force convection, we need to know what's the critical value of the Reynolds number, you know, to determine if the flow is turbulent or laminar. And for the natural convection, I told you is the Rayleigh number, not the Reynolds number more. So for the natural convection, what the critical Rayleigh number will be to determine the flow, natural convection flow is laminar or turbulent. Okay, this is the first question we want to ask. And the second question is that how Nussbaum number and this is for turbulence, okay? Because that all the Nussbaum number correlations we had before weren't able to work for turbulence case anymore. So what's the new, those correlations for Nussbaum number heat transfer, right, will be if the flow become turbulence. So this is the 2 questions we are going to talk about in the future classes. Okay, so I think I will finish today's class a little bit earlier. We won't have any homework today because that these 2 chapters I really do not have many homeworks for you actually. So if I have some, I will add it to the future homeworks when we are talking about more about the turbulence. Do you guys have any questions? If you don't have, we can finish the class.
I have a quick question about page 4 on the slides.
Which one?
On page 4.
This one?
Yeah, I have a quick question about the the UV average that's boxed at the bottom.
You mean here?
Yeah.
Okay.
It's how come we have the partial of V with respect to Y instead of U in the magnitude?
This one, okay. Actually, this one is not that because this UV. No, sorry, I missed a prime here. There's a typo here. U prime V prime. Okay. Actually, that you know that this U prime V prime V prime U prime, right? This should be symmetry. Okay, because that what I mean that the modeling of U prime V prime should be equal to the modeling of V prime U prime. I'm talking. Okay, but from here you won't see that symmetry here because that if you change U and V, you only have Y, not X, right? And the reason is that the equation I'm showing here basically is derived from the it's basically derived from the 2D cases. Okay, actually this partial V, partial Y actually is equal to partial U, partial X. Okay, so this is basically can be partial U, partial X, right? Something. I cannot remember the details. Okay, for Y is that, but what I can tell you is that this equation, you should not be using this equation in these cases. Okay, you should be using this equation. This is more the general cases where you should use actually. Okay, if you use this equation, if you do this U prime V prime, okay, that means that I equal to 1, J equal to 2, right? So this will should be equal to mu t of partial I equal to 1, so it will be u bar partial y plus j equal to 2 will be partial v bar I partial x. It should be this one actually. And this mu t can be replaced by this one here. Okay, and the vt can be lm square partial u bar and partial to the xj equal to partial y. Okay, with this one times this actually to this one. This is the correct one actually. And if you compare this one with this one, okay, you see that first thing is here is u partial y, and here is here is the v partial y. They are both correct actually. I cannot remember the details, but they are these two equations is very close actually. They're doing some approximation to do this actually. And the second one, you're seeing that you will have additional term here, vx, and we have two terms here if you times together, and you only have one term here. And the reason for that is that because when they group them, they just this additional term just will be absorbed in this constant. It's just like you can consider that this constant you just consider like this constant. Just like this constant here divided by 2 or something I'm talking. So there is a symmetry terms by 2 things. Maybe next class I'll give more details for this one. I really cannot remember how we get this actually. But I'm sure this is the one we usually use actually. This is more correctly one to use actually. Okay. Sorry for that actually.
Oh no, thank you. That answers my question.
I won't able to, I don't want to tell you the wrong thing, but I will figure it out actually.
No, I understand. I just had I was just confused about the I and J's, but you.
Yeah, if you get interested, you can try to read in this mixing lens theory. But most time mixing lens theory is they develop it from the 2D cases. Okay, and in the 2D cases, there is some because the continuity actually partial u partial x plus partial v partial y equal to 0. There's exchanging between these two. Their magnitude is same. I'm talking. So sometimes you see partial u partial x, but they just directly change it to partial v partial y. Is that they are that's the reason that you see sometimes they say partial v partial y. Sometimes they say partial u partial x here. I'm talking. That's part of the reason. Okay, but this tensor form is more general form that can be working for all 3D, even for 3D cases actually. Okay. All right. Any more questions?
Quick question.
Sure.
Would it be possible to get the latest homework grades before we go into the final, so we have an idea of where we are?
Oh, no problem. I already finished graded homework 5. Homework 6 I'm halfway, and homework 7 I will receive it. So
okay.
Before the next class, I will finish both homework 5, 6, 7. Okay. Homework 5 I will upload the grades to Blackboard tonight. Okay.
Okay.
And 6 and 7 I will finish it before the next class. Okay.
Okay. Thank you.
No problem. It's my fault actually. I'm a little bit late for that because this homework, this exam take me a lot of time to grade and prepare. Actually. Any more questions? Okay. So we can finish today's class. I'll see you next week. Okay.
Sounds good.
Okay. You're welcome.
Thank you.
Yeah. Thank you for attending. Okay, the class.
Have a good one.
Yeah, you too.